Okay, so we're going to finish this train presentation here. This is the end of the train economic assessment of absorption. We've already kind of done the economic stuff. They threw these slides in the end of this thing just to show, I guess, how good they think their control system is. And so we've got, I think there's 4 different slides here where they give some sort of strange operating condition to the absorption chiller. They plot out all the parameters for time, what happens to the performance of the engine, and how it's under control. So we may have mentioned this one last time. This simulates an airplane. So period, they we can look at it. Okay, so if you can hear me, I'm going to get out and change my internet and then come back. So hang on a second here. All that good stuff. Okay, so I should be able to do that. Can I?
Yeah, it should. I think it'll be okay if you're still in it now. Kick you out.
I don't know. All right. Well, it seems to still be recording. I don't know. We'll see. I hope it's there. Looks like, I think my cell phone will be okay. Okay, apologize for the interruptions. Okay, so air goes in the machine in this period. We see capacity drop, which is what you would expect because the pressures are going up in the machine. The temperatures are going up at the evaporator, so we get less capacity. And we can see down here, our chill water set point is, the same. Looks like it's maybe 44, 43, 44 degrees. And we were right on set point, and then the air came in, and because the capacity went down, the leaving chill water temperature went up, looks like maybe 2 degrees, something like that. And it took a while to get it back under control. But the point they make in the discussion is that, let's see, am I getting messages? No, that's good. Okay. Is that normally when the capacity went down, the old controls would have slammed the heat added in the generator up, which would have led to crystallization. But now the controls are smart enough to realize there's been an air leak in the machine. And see, we see the burner firing rate. This is, I think, on direct fired unit, actually goes down because the controls realize that, hey, we got air in the machine and we got to back off a little bit. So they actually reduce the firing rate a little bit and hold it constant. I mean, just about all the way across this plot. And as you can see, capacity at the same firing rate, capacity starts coming back because the purge is working and the pressure is going down the evaporator, and we get capacity back on the machine. And then eventually we start increasing firing rate once we get things back to normal, and we eventually pull back down to the chill water set point. Okay. And I would encourage you to read these notes. I think I had that one pretty good. So I've read over these a couple times, and so I think that one's okay. far as reviewing it any further. Okay, so this is a pretty aggressive test. So what they're doing now is they're going to monkey with the cooling tower, the temperature of the water leaving the cooling tower that's coming into the chiller. And they're going to start over here, oh my goodness, at 105 degrees. Well, you know, we usually expect to see 85. And so 105 is pretty darn aggressive. And then over, I think it's a 20-minute period or something, they're going to drop it, or it looks like about 25 minutes. They're going to drop it to 55 degrees, which is a 50-degree drop. So let's see if we can screw up this chiller, you know, let's do our best. And it's pretty impressive that they put it through this rigorous of testing. So what happens, and this is described in these notes down below, but during the steepest part of this descent, the machine controls just shut down the machine for a short period of time. And so I guess that's in here because you see that, well, now this is on restart. Okay. So we see here's entering water temperature, leaving water temperature. So initially it goes down and then it comes up. Well, I think they say there's a 6-minute period here where the machine is just shut down. It just doesn't feel like it can deal with it. And then it brings it back online and ramps it up slowly. And you can see the evaporator leaving water temperature at a little spike here, and that's the result, I think, of the machine being down. And then they ramp this down a little bit slowly so that they don't just go crazy. And I don't know, we can look and see. This first paragraph, they're just talking about what they did. At the 10-minute mark, most drastic drop in condenser water, machine actually shut itself down due to risk of crystallization. Reset, came back in 6 minutes, which is pretty good, and then it ramped it back up. So, whoops, well, that's no good. And they talk in here about train's able to, their control system is much better because of all the VFDs on the pumps, and they can make instantaneous changes. And so that helps to shorten the thermal flywheel effect or the response of a typical absorber. Train horizon absorber reacts up to 10 times faster than machines without this type of control. And yes, this is a commercial for Train. So where the other guys are, these slides have been out there a number of years, so I expect all the manufacturers probably have this stuff these days. Okay, so here's another fairly extreme. So this is simulating poor cooling tower temperature control. And so you see the seesaw pattern. This is what's really being changed. And then we're going to look at the response of the chiller to it. So we're going to ramp from 95-degree water down to 65-degree water. And I don't know, what is that, a 20-minute cycle or something? Probably says down here. And so we can see the evaporator. So this is the chill water coming back, entering water temperature. And then this is the leaving water temperature, which really, you know, is fairly well controlled. You see a little blip. And of course, the set point stays constant throughout. Oh yeah, the other point they make here, this set point is 39 degrees. Well, back in the old days, there's no way. I think 42 used to be the lowest that you could get out of an absorber. And so now with the better controls, we're able to get 39 degrees, which is actually pretty impressive from an absorption machine. Let's see what else they talking about here. There's the fluctuation. There's the 39. I guess that's all on that one. Okay, and here's another scenario. Here they're going to vary the evaporator flow rate. And so that's the chill water flow rate. Now, I mean, when I first started in this business, you know, way too many years ago, probably 30 years ago or so, Nobody varied evaporator and condenser water flow rates. It's just the machines. I mean, it just wasn't, it just was something you just didn't do. I mean, these are big machines, even the centrifugals, you didn't do that. Well, these days, through all the simulation tools and people studying this stuff and working and better controls and all that, um, people that look at total building energy use, they've realized that, hey, during less than peak cooling load, which is most of the time, we don't need the full design evaporator chill water flow rates. We can back off. And so with VFDs on pumps and good controls and all that, so we can start modulating back. Now, the chiller manufacturers on all these evaporators, absorption and other, are going to give you a range that you can't go below. You can't go above a certain velocity, and that has to do with tube erosion. And you can't go below a certain amount because you just can't transfer enough heat in order for the thing to be effective. At slow enough flow rates, the convection coefficient starts deteriorating, and there's just a minimum limit. But within that limit, you can modulate chill water flows, and people are even starting to modulate condenser water flows a little bit. So you can see what they've done here. So we start over here. Here's our flow rate over here. There's 1200, 1400 GPM all the way down to 600 GPM. And so we're starting over here at 1200, and then we take a step change down to 800. And you can see the actual leaving chill water temperature through all of this doesn't vary very much. I mean, it's pretty darn good control. And so then you can see your return water temperature shows more of an impact than your leaving water temperature. And so there's just doing these step changes and looking to see how that leaving water temperature varies. And the biggest one, we go from 1400 down to 600. Wow, so that's like a 60% reduction. That's pretty aggressive. And we say when they first do it, you get a dip. You're going to get some colder chill water because you're not putting as much evaporator flow through the evaporator. But generally speaking, it handles it really well. So that's pretty impressive. Okay, controls, sensors. And so, they're adjusting with those VFDs. So they say you can't do that on any other absorber, but in these days, I expect you can. Okay, we're almost done here. I think this is last slide. So, but there is some good points made here. When are we seeing absorbers? Well, these hybrid plants, and that had to do, in our economic example, with saving demand cost during a peak demand period of the day. And there are places in the country where that demand charge probably is between $24 and $28 a kW. Now, we're not that high in Tennessee right now, but if you go to the East and West Coast, power costs are much more expensive. And so this becomes much more attractive to them. Now, the second bullet under hybrid plants is something that any hospital is going to be interested in. I know CRMC over here, this being able to maintain cooling, adequate amounts of cooling in your hospital, your ERs, your emergency rooms, all over, intensive care units, all that sort of thing, because if you get a good power outage, I mean, something can happen. They could be out. It was out for, I missed the second half of the Super Bowl. Power at my house went out from halftime, halfway through the halftime show, until about 10 minutes until 10 on Super Bowl Sunday. And at first I was upset, but then when I saw what happened in the second half, I didn't miss much. And I didn't bet, so I wasn't that passionate one way or the other. So, but if this happens in a hospital setting, people get pretty darn upset. And so, with the power's out, if you've got a centrifugal chiller, that's a 600, 800 kW load. I mean, that's a lot on your emergency generators. But if you have an absorption unit, guess what? If you're burning natural gas, or your boiler's burning natural gas and you're making steam or hot water, uh, the natural gas keeps flowing, man. I mean, the gas is going to be there, and the amount of power it takes to run your boiler or to run a direct fired chiller is nothing. You know, you're talking, I don't know, 20, 30 kW, which is easy to pick up on the emergency generator. You know, the biggest load then is your distribution pumps. Make sure you can distribute it through the building. So having an absorption, a good size absorption capability in a large medical center makes a whole bunch of difference. And we toured Vanderbilt a couple of years ago. They've got some gas turbines, they make cogen, and they also have absorbers. Okay. And I'll tell you one thing they have a centrifugal chiller that's powered by a steam turbine. And the guy running the plant said, that's my favorite. I like that one better than the absorber, because he said we do sometimes have issues with the absorber. But that gas turbine, man, I mean, all I got to do, so long as I can keep my boilers online making steam, you know, so I'll put the steam through the turbine, that turns the compressor on the chiller. There you go. So that's another option. And I actually have a spec sheet on, I'll try to remember to email out to the class. So that's a big issue. Any critical application, if you're making semiconductors or something, wow, you got to have perfect environmental conditions for those things to come out right these days. And so having some absorption capacity in that chill water plant would be a good idea too. And there's lots of other critical applications. Okay, and then I'm gonna just review these notes down there. This lower tower GPM. There's some good numbers down here I want you all to look at. Okay. Low cooling tower flow is another something, I guess, idea that we're seeing in large chiller plants. So the old standard condenser water ratio, you should know this. This is one of the things sometimes that we pound home in the first course. But so on a centrifugal, and when you run the carrier program, when you create a cooling tower, it's going to default to 3 GPM per ton, because that's the old golden number for condenser water flows on centrifugal chillers. All right, they say electric, I guess it's a scroll and other types too. I just always think about the centrifugals. That number is being challenged. There are train engineers newsletters where they talk about going to 2.4, 2.5 GPM per ton as on the electric chillers. And that's, again, an effort to change or to save pump energy. And with the VFDs, you know, you could, under peak load conditions, go ahead and move it up to 3, and then under reduced load conditions, move it down to 2.4. And I mean, I think I've seen numbers as low as 2. Well, over a course of a month or several months or part of a year, that's a lot of energy, because, you know, on a big chiller, you're pushing quite a bit of water. I mean, you know, a 1,000-ton chiller, it used to be 3,000 GPM. Now it might be 2,500, 2,400 GPM, at least during parts of the year. And the old standard number for the absorption, remember, we need more cooling tower capacity for the absorption, right? Because we have the absorber, which is generating heat. That's an exothermic reaction. And then we have the condenser. So we typically come in at 85 and go out at 103, whereas on the centrifugal, we would come in at 85 and go out at 95. Those are kind of standard numbers. And some of those numbers are being challenged too, to increase the range so that you can decrease flow rates. But at any rate, the old number on the absorber was 4.5 GPM per ton. And you need to know that. I mean, that's part of, you know, what you're in this class to learn. And if you look if you create a cooling tower from the chiller plant in the HAP program, that cooling tower, if it's for an absorption chiller, it will default to 4.5 GPM per ton. You can set it on whatever you want to within, I'm sure there's some range. But so they're showing here that the trained direct fired absorber, they're down to 3.6 GPM per ton, which is, that's what, 9/10 of a gallon per ton. That's quite a bit of water on a big machine. So the comment is there, we lose about 1% in capacity and efficiency on the chiller, but because of the pump savings and everything overall, we make the system more efficient. So these are the issues that are being researched and pushed forward to try to reduce overall HVAC system energy use. Okay, so that's pretty good. And I think, there we go. So that's the end of this presentation. So let me go to our next one. And okay, well, I'm going to show you this first. So let's see. So I sent you this. You can thank me later. It's 117 pages from Marley. Now, Marley, who's owned by SPX now, is one of the, stalwarts in the industry. BAC, Baltimore Air Coil, and Marley are probably the two biggest players, and there's some other significant players in the market. Those are the two that come to mind right now. We'll get into this a little bit. I'll give you some read. I'm not going to ask you to read 117 pages, but this is a great reference for you to keep and hold on to, because you never know. You may be asked to develop some expertise in cooling towers down the road. But there's some psychometrics here that we'll look into a little bit, and just some pretty good stuff. But that's not today. That's a preview of coming attractions. Okay, so we're going to go over as much of this as we can get to today. This is one of those presentations that I shamelessly stole off of SlideShare a number of years ago. I was looking for just a good general introduction to cooling towers and figured there was something out there. And this is created a United Nations energy program, I think. So I guess this has been given all over the world. I don't know. It was developed in 2006, but the fundamentals don't really change. So we'll go through this. There are a few bullets in here. I didn't write this, that I'm not 100% sure what the guy's trying to get to. They're pretty cryptic. So there's a few of them I'm going to just pass over because I'm just not sure what he means by them. But in general, this is pretty darn good, especially the first part. So we'll start into this. Another thing I'm going to do is I'll send you log-on information to, I have accounts with Marley and BAC where you can actually select cooling towers. And so I'm going to send you logins, and we'll have some homework where you actually get out there on the web and select some cooling towers based on, we may probably do it for our building that you've been doing simulations on. And I also have a second simulation assignment that'll come out shortly. And I have been grading. I think I emailed out 3 or 4 people. When I grade it, I respond to your email where you send it to me, and I send you your grade and a few cryptic comments. Most of these are, most of these that I've looked at are very, very good. There may be 1 or 2 that, there's somebody out there that was having trouble downloading the program. I'll be happy to get with you, or we can get Chris Mills with you. He's probably better than I am, but one of us, most people have been able to do this. So, I think it's really to your benefit to get this program and learn a little bit about it, because it's a good program, and you just never know where life's going to take you. You may think, well, I'll never wind up doing this. And then, your first job is sizing chillers and cooling towers because that's what you can find. You never know. So at any rate. Okay, so introduction. Okay, so this is kind of a generic drawing of a cooling tower. And we're going to go through all of this in more depth and detail, and I guess you probably saw some of this in thermo. I don't know. But basically, this heat exchanger is probably our chiller. It doesn't have to be. So in a lot of industrial plants, um, we have process stuff, the welding issues, furnaces, I mean, we're working with a company in the East Tennessee that is tempering glass, and they're heating furnaces up to 700 degrees C in order to temper that glass. And they actually provide cooling tower water to certain sections of that furnace where the water just gets pumped through it to keep, the structural members from deteriorating by getting too hot. And so that happens. There's lots of reasons, lots of things out there in the industry that have to be cooled. So you see cooling towers for not only HVAC applications, but for other things as well. But anyway, so we have some sort of a heat exchanger. We got some kind of a heat load that we're going to have to cool away. And so, our cold water falls down into the bottom called the well or the basin at the bottom. So this is the water that's fallen down through the tower. So it's cool. So if we were to pick a number, we would probably say, oh, I'm going to assume that's 85 degrees at design, because that's a pretty standard number. But it doesn't have to be. I mean, it could be 100 degrees. I mean, it's just whatever the system designer, spec'd it out to be based on the process load and the size of the tower. So we're going to pump up through there. We're going to pump. So this would be our condenser water pump. If it's a chiller, pump through the condenser with a heat load. So typical number, come in at 85, come out at 95. And we go up to the top of the tower where there are distribution basins. Okay. And so basically that water spreads out all the way around this. And that basin will probably have a depth of 4 to 6 inches of water. Okay. And then, of course, different types of towers may be configured a little bit differently. And the idea is we want to distribute that water, and there's some kind of nozzles, some sort of spray system here to distribute that. And we typically have fill. Now, there are towers that don't have anything in here, but I would say 98% of the towers in the world have some kind of fill, and that's to increase the contact area between the air and the water. That's the air passing across either counterflow or cross flow, and the water's falling down. We get some evaporation going on a little bit, percent, something, and that cools the rest of it. And I mean, there could be some convective action, because this air, it could be 50 degrees, in which case that's going to tend to cool it down, but it also could be 100 degrees in the tower, so that could tend to heat it back up. So the tower has to operate no matter what and provide that minimum tower water temperature. Okay, so we got air coming across and up, and we got water falling down. We get this evaporation, and so water can come out of this thing. There's a couple of ways. One, evaporation. So you got molecules. Drift, because this configuration shows what we call an induced draft fan. So you got a propeller fan in here that's blowing, turning pretty quick, and it's blowing air up through here. Well, it's going to pick up some droplets, and it's going to go. That's called drift. So it's going to blow some droplets out of the top of that thing. Okay. So and then we've got blowdown. So I say we're putting in makeup water that has minerals and stuff in it. And when this stuff evaporates, the evaporation doesn't take any minerals with it. Now, the drift will blow some minerals out with it as well, but the evaporation is much larger than the drift. And so if we don't do anything, well, first of all, this thing's going to run dry. And so, we got to have makeup water, but it's bringing in minerals, and they're going to concentrate in here. So we have to do what we call blowdown, which is just blow some of this water, throw it away in order to keep these minerals from building up too concentrated, because they will scale. They'll form a scale on the tower, and eventually that scale is like rock. It's just minerals. Eventually the fill will collapse if you get too much on there, because the stuff is heavy. So we got that going on here as well. Okay, I think that's pretty good for. Yeah. Okay, so he's going to list components. So frame casing, support exterior enclosures. The fill, there's actually different types of fill. When we get further into this, there's a slide or two that gives some numbers, some characteristics of the fill. And they actually list a third type of fill. But the standard, or the old time, was splash fill. And in the old days, they used to make that fill out of some sort of exotic wood. I think it was like teak and stuff from over there in the rainforest that wouldn't deteriorate because it's sitting there wet all the time, you know. And there used to just be these little slats. They kind of stack them in this pattern to have lots of gaps in there, and the water would splash down on top of it and break up into smaller droplets and all this. And now we have film fill, which is definitely more effective. And this is like the plastic. I think Dr. Languri's got, there's some pieces of fill over in the lab I can bring in and show on the camera here. But it's like PVC stuff, and it's kind of like a honeycomb deal. And I mean, it's a lot goes into designing these fills, especially the film fill. Anyway, and the film fill is typically better in most applications these days. And that's a retrofit option, is to take an old splash fill tower and retrofit it with film fill, and you get more capacity out of the tower. And then, of course, we've got the cold water basin, receives water at the bottom of the tower. That's where the blowdown comes out of. It's where the makeup water goes into. Okay, drift eliminators. So up at the top of the tower, we get some better pictures. Here, these little crinkly guys up here at the top, what these are, they're some sort of just sheet metal or probably heavy duty plastic these days. And the idea is they make this air is being blown up through here at significant velocity, and it's carrying these droplets with it. Well, we want to keep the droplets inside the tower. So we just make this thing, you know, change direction a couple times. The droplets hit on the side. So we make that air kind of, it goes up a little bit, and it goes sideways, and then it goes up and it goes sideways a couple times. And so most of the droplets hit and coalesce on the drift eliminators, and then they fall back in the tower. So that's what a drift eliminator is. So these days, if you buy a tower, it's going to have a drift eliminator on them. Okay. Air inlet, well, we got to have some point that we get air into the tower. Louvers equalize airflow into the fill and retain water within the tower. So a lot of these things have louvers on the side. It kind of, as the air comes in, it gives it a definite profile and orientation into the tower so that it flows through in the most efficient means. Nozzles, we've got to distribute that spray water inside the tower to get it across the fill effectively. And we got to have some kind of fans that force air. We'll see if we can have forced draft fans that blowing in, or we can have induced draft fans that are sucking out. All kinds of different configurations are possible. All right. So types of cooling towers. Okay, so this, I always get a chuckle on this one. These natural draft cooling towers, these are the big boys that you see like at the nuclear plants. And, you know, when somebody that doesn't like nuclear energy wants to make a poster, what do? They take a picture of the cooling tower with this big white plume coming out of the top and say, look at this terrible pollution. Well, you know what that white plume is coming out of the top of the cooling tower? It's a cloud. It's water vapor. And so, oh my gosh. I mean, it's fine with me if you want to protest nuclear energy, but good Lord, don't show your ignorance, you know, of cooling towers when you're doing it, because that cooling tower is not polluting. In fact, that parabolic cooling tower is built that way so it doesn't even need a fan, because that large shape and the height induces the flow. And that's why the electric utilities are willing to invest in them, because otherwise you would have probably a couple thousand horsepower of fans down there blowing that much air through this tower. And well, gosh, if we just build this thing, 200, 300 feet high out of concrete and all this stuff, so it doesn't fall down in this nice parabolic shape, the air will flow by itself. And so that cooling tower that's being advertised as an emblem of pollution is really reducing pollution by not running electric motors to make the cooling towers work. It's just amazing, the stuff you see out there. But anyway, so natural draft cooling towers, hot air moves through the tower, like it gets induced through there by density variations. Fresh cool air is drawn into the tower from the bottom, no fans required. Concrete tower less than 200 meters, which is 200 meters is what, over 600 feet or less, something like that. And used for large heat duties like large power plants, like large nuclear plants where you've got a whole bunch of heat you got to dump. And you don't have a lake nearby to dump it to. So you're going to dump it to the air. So we can do this with a cross flow geometry or a counterflow. So on the cross flow, the air comes in and basically flows across the fill and then turns and goes upward. And in the counterflow, it's kind of like the air inlet is beneath the fill and it gets pulled in and then it turns vertically and goes upward. I don't really know all of the ins and outs as to when you would want one and when you would want another. That big Marley document has got, several pages describing these. So that would be a good place to look for more information about the natural draft cooling towers. Okay, I think we've talked about most of that. Okay, then we get into mechanical draft cooling towers. So we're going to have a good sized fan because we got to move some air through this thing to make that evaporation happen so that we can cool. Now, when you select a tower, it's kind of interesting. That's why I like to get you into the selection. You give the selection software the flow rate and like an entering water, a desired leaving water, and it'll come up with 10, 15 different towers. And you look down there and you look at the fan size. And, there may be one that has the smallest fan size is 20 and the largest fan size is 50. And you go, well, crap, what's going on here? Well, what's happening is the physical size of the tower is changing. So if I buy a large enough physical size tower, I don't need such a big fan. But that increases my first cost. If I want to reduce the overall energy footprint on this thing, I would buy the largest size that I could justify, which would come with the smallest fan. But of course, first cost people, they say, man, that's too much. I could spend $100,000 on the cooling tower. Yes, you get me one cheaper. Well, yeah, I get you one for 60, but it's going to have a 50 horse motor on it instead of a 20 horse. Well, I don't care about that. I don't have to pay the energy bill. I'm going to make my tenants pay the energy bill. So guess which one goes in? So you're sitting there blowing way more air because you don't have much surface area in the tower, and you got to really, spend the money to move a higher volume of air through to get higher velocities to make the thing work. So that's kind of one of the games that we play here. Anyway, we're going to have a significant size fan. So water falls over fill surfaces, spread out the water to maximize heat transfer. A lot of different parameters go into determining exactly how the tower is going to operate in any given day or any given condition. Large range of capacities, and we can group cells together. There's some, like you may see a large cooling tower that has 6 fans, and so each fan would handle a section, and that section is called a cell. So it's very common, like Tennessee Tech. if you go down there and take a look, they've got some in-ground ceramic towers, which are kind of strange. You don't see those all the time. And then they've got an above-ground tower, at least one, I think maybe two. And they're two-cell towers. If you climb up on top of them, they've got two fans. They're induced draft, so they got two propeller fans that pull the air up through there. So two towers, each are two cells. So that's kind of the nomenclature. Okay, and so we've got three types. We've got a forced draft where we blow the air through the tower. And we've got induced draft, cross flow, and we've got induced draft counterflow. So these are kind of the three types that we'll be looking at here. We got pictures of them, all that sort of stuff. Okay, so this is the forced draft cooling tower, and you see down here at the bottom of the tower, we've got a centrifugal fan that's pulling air in, and it sits down here in the compartment, and it can blast air up through the fill into this chamber to spread it out, and then it penetrates up through the fill with the water falling down in counterflow. Okay, and we've got some characteristics over here. So air is blown through the tower by a centrifugal fan at the air inlet. Advantages suited for high air resistance, and fans are relatively quiet because this fan can be pretty much enclosed in the structure of the tower. And, you know, and then the blast is going up through the fill, which tends to muffle the sound as well. Disadvantages, recirculation due to high air entry, low air exit velocities. Okay, recirculation. So that's something we'll read about. You might want to look at in the big train fundamentals and see there's a lot of discussion on recirculation and how to lay out towers relative to moisture. But the idea is this air coming out of here, well, first of all, the velocity, the high velocity is at the blast of the fan. So by the time we work our way across the fill and up through all this water, across the drift eliminators, we don't have a super high velocity at the top of this. And of course, this water is essentially, this air is essentially saturated with water, because guess what? That's what we want it to do. We want it to come in less than saturation, and when we want some evaporation to take place, and we want that evaporated water vapor to be carried away by this exit air. Well, if I don't have much velocity here, maybe I have a wind blowing across this thing, and I blow this saturated air back down around, and it gets sucked up by this centrifugal fan again. And so that air gets recirculated back into the tower. Well, that can't be good for tower performance, because here I'm putting saturated air, or some portion of the air going in is already saturated, and it's not supposed to be, you know, unless I sized it for it. And so that's going to be detrimental to the performance of your cooling tower, because the saturated air can't evaporate any more water into it. It's saturated, it's done. And so it's got to go on out and mix with the air in the atmosphere. And we got to have some nice, good ambient air that did not go through the tower down here around this fan to get pulled in. So that's what we mean by recirculation. And that's not a good thing at all. And there'll be some more discussion of that. The other thing that you'll see, and he didn't put this on this slide, but for the given size and capacity of tower, this centrifugal fan will be a larger horsepower than if it was an induced draft fan. That's almost always the case. Okay, because I guess because you have this very high velocity that you're coming out of this thing, and it has to fight its way through the fill. Propeller fan is, or the induced fan is up here, and I think the velocity through the fill is probably a little bit less. And anyway, the induced draft fans tend to be lower horsepower for the same capacity. So if I was doing this slide, if I had the PowerPoint, I had the PowerPoint on this thing and it kept locking up my computer. There's something corrupt in it. And so I was able to find this PDF version. And so it still works for what we need it for. Okay, so that's the forced draft tower. And then for the induced draft, this means it's got the propeller fan at the top of the fan and it sucks air up through the fan instead of blowing air on the discharge side through it. So we got cross flow and counterflow. Advantage, less recirculation than forced draft towers. And that's because we have the high velocity. So here's a induced draft fan. And so say the fan is right there and it's blowing the air. So that's the highest velocity of air moving because of the operation. This fan is on the discharge and it's right there blowing. So that air gets, that saturated air gets blown way up above the tower and hopefully doesn't get re-entrained or recirculated back in the sides. And then disadvantage, fans, motor drive mechanisms require weather, that shouldn't say weatherproofing, sorry. And so what you'll see, and of course, you know, now it's possible to have the motor outside. And, you know, you can have a pulley arrangement or you can have a drive shaft. A lot of these motors are up in here and still have a pulley, a drive shaft, some sort of a drive box on it. And they're sitting there in all that moisture all of the time. And that causes an issue. I know we did some energy work for the TVA power plant at Magnolia, Mississippi, had 3 combined cycle plants down there. And they had, each unit had, was it a 5-cell cooling tower with 5, each one was a 200 horsepower motor, something like that. And they had a drive box on them. And the motors were outside of the flow, but the drive box was in the flow. And I mean to tell you, they were constantly doing maintenance on those drive boxes because the seals would go. There was just such a moist environment. They couldn't keep water out of them. And it was like $150,000 every time they had to replace one of those drive boxes. And so we were looking at going to a direct drive situation with VFD control on those. I don't know if they ever did that, but there was some savings there. Let's see. Okay, so I think we got all that. And this is our first picture. So this is induced draft. And again, induced draft means we're sucking air through the tower and we blow it out the top. So air enters the bottom, exits the top, uses forced and induced draft fans. Well, it uses, wow, this is an induced draft. So that's, I think that's a misnomer. But we can see we've got 2 different varieties here. The one on the left shows a fill, and this one shows no fill, just kind of an open canister. But again, I don't believe that you're going to see many of those. So let's see, on the right, induced draft counterflow tower with fill, and the other without fill. Okay. Okay, so this would be cross flow. So induced draft, cross flow cooling tower. And so here the air is going to sweep in the sides and kind of come across the fill as the water falls down. So it's considered cross flow. I guess you can have one of these with just one fill section. You don't, that would be a pretty small tower. They're out there, but for any significant HVAC application, this is what they usually look like. And this is the common type tower that you see. So we see our distribution basins over here on the side. These are drift eliminators. They've got them tagged in here. We got our sump, our cold water, where it collects in the bottom. We got louvers on the side. We want to direct that airflow at the proper angle so that it can come across the fill as the air is falling down. And of course, we've got our fan and all of that up here. So that's pretty good. Okay, assessment of cooling towers. Okay, my goodness. Look at all of the things, the parameters that we really need to measure to assess this. I think there's a good example problem in your thermal book on a cooling tower. I think I'll scan it and we'll look at it. I don't know. We might even work a homework problem on it. Who knows? Measured parameters. Well, the most important operational parameter, sorry, environmental parameter, is the wet bulb temperature. Because you can only cool air by evaporation to the wet bulb temperature. That's your temperature limit. Okay. So the more, if I can saturate the air, then I can cool it to totally saturated. Then I can approach the wet bulb temperature, but I can never get it colder than the wet bulb by evaporation. Okay, so wet bulb temperature is the one most important operational parameter. Dry bulb temperature certainly has an impact. You know, wet bulb temperature could be 70, and it could be 70, and I could be putting in, 60-degree air. No, I can't do that. But anyway, as that dry bulb temperature changes, that will have some impact on the performance. I guess if I had a 70, I could have an 80-degree dry bulb, or I could have a 100-degree dry bulb. And so, if this is in Phoenix, Arizona, where that wet bulb is going to be pretty darn low because there's not much moisture in the air, I get better cooling tower performance than I do in Miami, where the humidity is so high and the wet bulb temperature is going to be high. Okay, so then of course the cooling tower inlet water temperature, how hot's the water coming back from the process, and what's my desired cooling tower outlet water temperature, what's my exhaust air temperature, and then of course electrical readings, how much energy am I putting in the fan and the pump, what's the water flow rate, and what's the airflow rate through the tower. So there's a lot of parameters here to consider in the operation of a cooling tower. Okay, so let's go through some of this. Assessment of cooling towers, performance parameters. So these are all things that we need to define and make sure that we understand. This is the terminology of the cooling tower. So here we go. If you look over here, this is the typical kind of a diagram. So this red line is our hot water temperature. So this is, say, coming out of the chiller back out to the tower. It could be 95 degrees, whatever. And this is the cold water temperature that we achieve by the operation of the cooling tower. So the typical numbers here would be 85 or 95 in and 85 out. So that would make the range 10 degrees. But, whatever the hot water temperature in minus the hot water temperature out is the range of the cooling tower. Okay. High range is good performance. I guess that makes sense. I mean, put it in hot, you want to make it as cold as you can to get it out. Okay, so that's range. Then we're going to do approach. Okay. So if this tower was infinitely large, I could cool that water to the wet bulb temperature. If I make it bigger and bigger and bigger and bigger, if I consider it to be infinitely large, then I can get it all the way down to the wet bulb temperature. Well, and that's the theoretical limit. Well, guess what? I can't afford an infinitely large cooling tower. The budget just not there, So I have to pick one that's not that good. And so then the difference, and this is usually defined at the design condition, which is, the worst condition that you're selecting the tower to be able to satisfy. Okay, so then, but I mean, you can talk about the approach at any point in time, and by definition, the approach is the cold water exit, the cold water temperature that we're achieving by cooling through the tower at the bottom of the tower minus the ambient wet bulb. So that's what we mean by approach. And of course, low approach is good performance because we're getting closer and closer to the theoretical maximum coldest temperature that we can get the water to. Okay. I think that's good. Okay, effectiveness. This is just a measure of kind of how good are we doing? What's the design effectiveness, and then what's the actual effectiveness, at a given situation. So we're going to take the range, which is the difference from the red line down to the cold water line, and just divide it by the distance from the cold water all the way down to the ambient, the wet bulb temperature. Or so that's range divided by range plus approach. And we're going to multiply it by 100 so we can have that as a percent. And of course, if I had my tower that's infinitely large, well, my cold water temperature would be my wet bulb temperature. And so I would have an effectiveness of 100%. So yes, you go through that and just to make sure that it makes sense to you. So you're never going to have a 100% effective tower. It's not possible. Well, it's theoretically possible, but you're never going to buy one that big, so it's not going to happen. Okay, cooling capacity. This is pretty easy for a mechanical engineer, right? M dot CP delta T. You guys, I'm pretty sure you guys can handle that now. And of course, these slides were done by a metric guy, so he's all into kilocalories per hour. Oh, he does mention tons of refrigeration or BTUs per hour, whatever system of units you want to. But so it's just M dot, mass flow rate of water, kilograms per hour, pounds per hour, times the appropriate specific heat, times the temperature difference. And that'll get you probably kilojoules per hour, megajoules per hour, or BTUs per hour, and then you can convert that into tons of cooling if you want to. Okay, evaporation loss. There are some standard numbers that get used, and the ones I use are not these because they're in the US units. I've got another little handout I'll send you with some other numbers in it, but I mean, there's nothing wrong with this. I mean, I've never checked this. I trust it's correct, but this would let you calculate an approximate evaporation loss. How much water do we have to evaporate to make this cooling occur? And they're saying theoretically it's 1.8 meters cubed for every 10 million kilocalories of heat rejected. And then he's got a little equation down there, 0.0085 times 1.8 times the circulation rate, meters cubed per hour, times the temperature difference. And probably need to check units on that. There may need to be a specific heat in there. I've not checked the units on that. But if that's 1.8, it looks to me like we need a specific. Sometimes in slides, people leave out specific heat. And it's kind of interesting. Say let's see, what's the specific heat of water in metric? It's not 1. Say in US units, the specific heat of water is 1. And so people leave it out all the time. Well, the units won't work without it, but you get the right answer because you're just not putting a multiplier of 1. But in metric, what is it, 4? Something like that. I don't do enough metric calculations in water to remember. I mean, we can look it up in the thermal book easily enough. But I think we probably need a specific heat in that equation. So you would want to check into that. But like I said, I'll give you another handout here. But anyway, there are equations out there where you can calculate the evaporation loss. Okay, some other terms, cycles of concentration. And this is the ratio of dissolved solids, or you can think of that as crud, in the circulating water, you know, like in your loop that you're putting through your chiller and your cooling tower and all that, to the amount of dissolved solids in the makeup water. Okay, so that gives you an idea how concentrated cycles of concentration, how concentrated your level of minerals or crud is compared to the level of the makeup water, which you are using to dilute those impurities in that circulating water. So, you know, think about it. If you were just running water through the tower one time and throwing it away, then this cycles of concentration would be 1, because all you would have in the system would be makeup water. Okay? And so if whatever the amount of dissolved solids in the makeup water is, if you're circulating twice that in your system, then your cycles of concentration are 2. If your cycles of concentration are 3, you're circulating 3 times the amount of crud in your system as in the makeup water. Now, if you're circulating, sometimes people operate these things at 8, 6, 8, 10. Well, see, the higher that cycles of concentration, the less water you're using, but the more likely it is that you're going to scale something up because you've got all these minerals circulating inside your system. And so one of the recommendations that you'll see is that people add chemical treatments to the water so that they don't have to blow down as much water, so that they don't have to make up as much water, and that saves on the water bill. And, you know, so long as you don't scale things up, you're okay. But if you don't put your chemicals in right or keep your chemical balance right when you're running high cycles of concentration, you're likely to scale something up. And if you scale up a cooling tower, you got a big problem on your hands, because those things got to be chemically treated, or if they get too bad, this film fill is like PVC plastic. And you start hanging a couple 1,000 pounds of rock in the form of minerals on that, guess what? It collapses. And then you get to replace it. So then you get to take your tower completely out of service, drain it, take it apart, pull all the fill out, put new fill in, put it back together. So you're talking probably, I don't know, $30,000 to $50,000 repair, all because you were trying to save some water by running high cycles of concentration, and you screwed up your water treatment. So that stuff's out there, and it can happen. Let's see, and then depend on sinus concentration, evaporation loss. So you can calculate a blowdown by the evaporative loss divided by 1 minus cycles of concentration. I don't have any real experience with that equation, but I've seen it, so I trust it's good. Okay, liquid to gas ratio. Okay, so this is the ratio in terms of the same units. It could be pounds per hour, it could be kilograms per hour, of the ratio of the water airflow divided by the air mass flow rates through the tower. So that's like a parameter on the cooling tower. Cooling tower manufacturers, when you buy a tower, you know, that's a parameter that you can specify, or that they'll tell you on a given tower what the L over G ratio is. And there are certain ranges for different types of towers and all that sort of thing. So, you know, if you think about it, if you just look at a simple energy balance idea, the heat removed from the water must be equal to the heat absorbed by the air. Because guess what? It's the air that's doing the cooling. So the air comes through, it's got its mass flow rate. The water falls through, it's got its mass flow rate. And of course, there is a difference now. The mass flow rates really change a little bit, right? Because the air picks up moisture and the water loses a little bit of moisture. So maybe that's being kind of swept under the rug in this equation, because we don't have a liquid flow in and a liquid flow out, which is maybe 0.5% less or something. But anyway, so we're kind of glossing over that. But when you look at those equations, that L, see, that's M dot, and you don't see CP. The CP is there. It's got to be, because this is heat transfer, right? So that's M dot CP delta T on the liquid side. So L is the mass flow rate of the water. You'd have to have the specific heat of the water times the temperature difference. And that has to equal G, which is the mass flow rate of the air times the enthalpy difference. And so the air side is completely correct. But on the L side, you need to write in C sub P in there. Again, I don't know why. Even some of the Marley literature I've got on cooling towers, they just leave out CP. I don't know why. It's wrong, but I don't know. It just they assume that you know that. Okay. So that's the L over G ratio. Okay, efficiency opportunities. I tell you what, that's pretty good. I think I know this Zoom stuff gets to be hard. So I think I'll go ahead and stop there, and then we'll finish this up next time. There's a lady that sells cooling towers in Nashville, Jill Rowan. I sent her an email to see if she might want to address the class. Just give you her take on cooling towers. She's really, that's her life's work, is selling and helping people with cooling towers. So I don't know. We'll see if she responds to me. So maybe Thursday or next Tuesday, we can let Jill do the presentation. I hope she responds affirmatively. I kind of think she will, but I'll let you know as soon as I find out. So I'm going to cap this off right now, and we'll, if Jill's not on next time, then I'll finish this and we'll move into some other stuff on cooling towers. Hope everybody has a great day, and we'll be in touch.